All right, we are on our last section of chapter 14. Chapter 14.3 is about, or section 14.3 is about the behavior of gases. So this will be our last section, and then next Tuesday you will have your chapter 14 quiz. Excuse me, next Monday. Next Monday is your chapter 14 quiz. All right, so let's begin. We're going to be talking about some special behavior of gases. Last time we talked about the special properties of liquids. Now we're going to talk about kind of how gases behave, the state of matter that is gas, how it behaves, or how they behave, gases behave. So we're going to recall that pressure is a force exerted per unit area. Pressure is a force exerted per unit area, and the units of pressure that we're going to be using are kilopascals, which is kPa, and or atmospheres. I'm going to actually write, this is kilopascals, just like kilograms, so this means 1,000 pascals, right? Just like kilogram, 1 kilogram equals 1,000 grams. 1 kilopascal equals 1,000 pascals. All right, so this is a unit of measurement for pressure. Another unit of measurement for pressure that we're going to use is called the atmosphere, and it's abbreviated ATM, atmosphere. So that can be confusing because there's an atmosphere in our above the earth, but what I'm talking about is the unit of pressure, atmosphere. We have a conversion here that we need to know. It is 1 atmosphere, 1 ATM equals 101.3 kilopascals. You're going to need to know that relationship. This is the relationship, like how if I give you my weight in pounds, you could find it in kilograms using a conversion, right? In dimensional analysis, like we've done before. But this is for pressure. So 1 atmosphere of pressure is the exact same thing as 100.3 kilopascals of pressure. All right. So pressure is equal to force divided by area. Or we can say pressure is equal to F over A. And the units of all of these things, we're going to have this in, when we use this exact equation, we must put pressure not in kilopascals, but just pascals. Okay? So that's another unit that we'll be using, but if you know, I mean, it's pretty simple. And the unit of force will be in newtons, and the unit of area is in meters squared. All right? So those are all the units that you must have these in when you're doing your equations for pressure. Okay. So some problems that you might see using pressure. Let's do an example problem here. Actually, sorry, really quick, I forgot to mention what an atmosphere is. 1 atmosphere and 101.3 kilopascals. This is the pressure at sea level. Pressure at sea level. All right. So this is about the pressure that you feel in Nouakchott right now. If you were below sea level, so let's say, okay, we're going to draw a little picture here. We have a town, and it has a beautiful mountain, and then we have the ocean here, right? And then if you come in this way towards the town, there's a big, deep valley. There's a valley over here. All right, so there's 3 locations in the town. There's the mountain, there's the ground at sea level, and then there's deep in the valley. All right, so at sea level, we're going to have 1 atmosphere of pressure, or 101.3 kilopascals of pressure. As we go up, as we rise in altitude, as we go higher in the sky, we feel less pressure. So this is going to be less than 1 atmosphere. And if we go down below sea level, this is going to be down, this is going to be more than 1 atmosphere. So as you rise into the sky above sea level, you are decreasing your pressure. As you go down below sea level, like in a valley, you are increasing your pressure. The pressure increases, right? So just so you know. And what causes pressure? Pressure is caused by, I'm going to make a note of this. This isn't in your book, but I think you should know this. Pressure is caused by gas particles colliding with one another and the objects that are surrounding the gas and objects around gas. So what causes the pressure on you right now, why you feel 1 atmosphere of pressure, is because there are little molecules of gas. There is a certain number of molecules of gas that are running into the side of your head, that are pushing in on your eardrums, that are making you feel pressure right now. Well, you don't feel it because you're used to it, but if we went high up in the sky or low down in a valley, we would feel it because we're not used to those pressures. There would be a change in pressure, therefore we would feel it then. So the thing that causes these changes in pressures is the amount of gas, basically. So you could imagine it as, if I'm going to draw, let's draw some gas particles. These are way too big. So this is the normal, this is the normal amount of gas at sea level. And then as we rise, the gas particles become fewer. There are fewer gas particles high. And as we go down into the valley, as we go down, well, there. So as we go down into the valley, the number of particles increases, okay? As you go up into the atmosphere, or as you go higher in altitude, it's called, the number of particles decreases. So if there are fewer gas particles up here at a higher altitude, there will be fewer collisions, and therefore there will be less pressure. But if we go down further below sea level, into a valley, for example, we will have more particles of gas that will cause more collisions, and they will run into each other, into other things, and run into each other and into other things, and this will cause more pressure. Okay, so that's kind of the idea. I kind of jumped ahead to do problems before I really fully finished my thought here. So that's pressure. This is the equation that we're going to use to solve some problems with pressure. So I'm going to give you those problems. Let's do a couple example problems. All right, so here is our example problem. The force exerted by a gas inside a balloon is 129,125 newtons. The area inside the balloon is 1.25 meters squared. What is the pressure in kilopascals inside the balloon? What we're going to do is write down our knowns, unknowns, and our equation. Like always, we will do every time in all of these problems. So our known, we know force is equal to 129,125 newtons. Area is equal to 1.25 meters squared. We're looking for pressure in kilopascals. You don't have to write in kPa, but just make sure you remember that. And the equation we have is pressure equals force over area. And now we're going to solve. So what we're going to do is just plug in for force and area. So we have 129,125 newtons. Divide that by 1.25 meters squared, and we get 103,300 pascals. So we're in pascals, remember. So in order to get to kilopascals, we can do dimensional analysis. We can say how many kilopascals equals 103,300 pascals. We know that 1,000 pascals equals 1 kilopascal. So you can do it that way, or if you can do it simply in your head, you can just divide this by 1,000. You don't have to do the dimensional analysis every time. So when you do that, you're going to get 103.3 kilopascals. All right? Okay, let's do one more problem here. It says that inside a container, there are 109.5 kilopascals of pressure. The area of the container is 0.95 meters squared. What is the amount of force that the gas particles are applying to the container? Or apply to the container, I guess. All right, so known, unknown equation, right? And we write down everything accordingly. We have a pressure of 109.5 kilopascals. So we have to convert this to pascals, and to do that, we're going to multiply it by 1,000. So we get 109,500 pascals. And we also know that our area is equal to 0.95 meters squared. All right, our unknowns are force. We're looking for force, and we're going to use the equation that we have been using. All right, now we can solve. We need to, first before we solve though, we're going to have to rearrange our equation by multiplying both sides by area, and then we'll get force equals pressure times area. So we're going to go force equals, and our pressure, which is in kilopascals, so that's 109,500 pascals, multiplied by our area, which is 0.95 meters squared, so that's supposed to be a 2. Plug this into our calculator, and we find that we have a force exerted by the gas of 104,025 newtons. This is our force. All right, so you're going to be responsible for doing some problems like that. Now we need to talk about these two special properties of gases, these two rules that gases kind of follow, or laws that they follow, I guess. So the first one is Boyle's law, and the second one is Charles's law. And you should kind of already know what these are based on, or because you've done the reading. But Boyle's law states that if we keep the temperature constant, so if we keep the temperature, we'll say at constant temperature, so constant temperature means the temperature is not increasing, the temperature is not decreasing, the temperature is staying the same. The pressure and the volume of a gas have an inverse relationship. So at constant temperature, there is an inverse relationship between volume and pressure. So what that means is if we have two balloons, here are my two balloons, and inside those two balloons I have the exact same amount of gas. Let's say I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 particles of gas in each balloon. The difference here is that the volume of the balloon is changing, right? It's decreasing. We decrease the volume of the balloon. So remembering that pressure is caused by collisions between gas particles and the container or the object around the gas, so in this case the balloon, what do you think happens to the pressure? Do you think there are more collisions in balloon 1 or more collisions in balloon 2? Well, there's going to be more collisions in balloon 2 because there's less space. If we have 10 students in the cafeteria and they have to run around as fast as they possibly can with their eyes closed, what are the odds that they will run into each other? Well, not super good. They'll probably run into each other. There will be some collisions. But if we took those 10 kids and put them in the bathroom upstairs, the girls' bathroom or the boys' bathroom, whatever one, they're the same size. If we put them in there and they have to move around as fast as they can, how many more collisions are there going to be? There's going to be way more collisions in the tiny space, right? So the inverse relationship is that as we decrease volume, we increase pressure. Or what if we had two balloons? We have balloons 3 and 4 here now. We're looking at balloons 3 and 4. And I put my 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so now imagine I take those 10 kids, those 10 students, and I put them out on the soccer field and have them run around with their eyes closed. What are the chances then that they're going to run into each other? Well, they're not as high, right? There's going to be less pressure in the big balloon. There'll be less pressure with a greater volume. There's a greater volume, but there's less pressure than there is here with a smaller volume, but greater pressure. So the other relationship, it's just an inverse relationship. As we decrease volume, we increase pressure, or as we increase volume, we decrease pressure. All right? And there's an equation that you're going to need to know for this. The equation is P initial V initial equals P initial, final. P final, V final. Okay, so this means that the initial pressure times the initial volume, we're going to do some practice problems, initial volume is equal to the final pressure times the final volume. So, and let me, you might also see me write this as P1V1 equals P2V2. You'll see it that way as well, and it means the same thing. So the first pressure and volume and the second pressure and volume. Okay, so these are the same. You can use either one, all right? Okay, so let's look at an example problem here. So a weather balloon has a volume of 100.0 liters when it is released from sea level, where the pressure is 101 kPa. What will be the balloon's volume when it reaches an altitude where the pressure is 43 kPa? All right, so we're going to write down our knowns, unknowns, and equation. Okay, so we have to imagine we have a weather balloon here, and we're starting at sea level, okay? And we're going to let that weather balloon go, and it's going to go up, 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 up in the atmosphere. As we're going up in the atmosphere, what happens to the pressure? Remember, this has a high pressure here, and we're going to have a low pressure higher up in altitude, okay? So what do you think is supposed to happen to the volume of the balloon? Well, if we're going from a high pressure to a low pressure, we're starting with a smaller volume, and we're going to increase the volume. The volume's going to increase, right? Okay. So let's write down everything we know. We know that the weather balloon has a volume of 100 liters when it is released at sea level. So that's our initial volume. VI equals 100.0 liters. And the pressure, initial pressure is 101 kPa. What will be the balloon's volume when it reaches an altitude where the pressure, the final pressure, is 43.0 kPa? And we're looking for what will be the balloon's volume. So what is the final volume? We know that PI VI equals PF VF. So we need to rearrange this algebraically to solve for VF. We will divide both sides by PF. Cancel. We get PI times VI divided by PF is equal to final volume. We'll plug everything in, and we find, that final volume is going to be equal to 101 kPa, that's initial pressure, times the initial volume, which is 100.0 liters, divided by the final pressure, which is 43.0 kPa. Be very sure that you have all of these in the same units, okay? That's going to be a tricky thing to keep track of. So be sure you keep everything in the same units. My kilopascals will cancel here, which is good because we want to be left with liters. So I find my final volume is going to be 235 liters. And to verify that you're right, make sure that your final volume in this situation, because you've drawn the picture and you've thought about the problem, right? You think it out. Okay, it makes sense that the volume should get bigger because we're decreasing the pressure, right? We're decreasing the pressure. We have an initial pressure and we're going to a lower pressure. So we start at high P, we go to low P. Therefore, we must start at a low volume and go to a higher volume because there's an inverse relationship because of Boyle's law. So think about, don't just memorize the equation. Think about what the law means, and then you'll be way better off solving these problems. The last thing we have to talk about in this section is Charles' law. And Charles's law tells us that at constant pressure, so when pressure isn't changing, at constant pressure, we have we'll say there is a direct relationship between temperature and the volume of a gas. So that means that as the temperature increases, so does the volume. And as the temperature decreases, so does the volume, right? So let's look at some examples and think about why this makes sense. If we're going to look at we'll look at our balloons again, okay? So we have two 1 liter balloons because we're not going to change we're going to start with two 1 liter balloons, okay? So we're going to have a gas in each of these. We're going to have 10 particles of gas again. 2, 4, 6, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, these are at room temperature and at sea level because pressure is constant. So we're at 1 atmosphere, okay? So we're not going to change the pressure. And make sure that when you're doing these problems over here, we say we're at, at T equals 20 degrees Celsius. I forgot to make sure that we have constant pressure or constant temperature always, okay? We're not changing the temperature in Boyle's law, and in Charles's law, we're not changing the pressure. So we're going to start with a 1 liter balloon on each side here. So we're going to start this at an initial temperature of 20 degrees. And yeah, okay, we're going to start it at an initial temperature of 20 degrees. We're going to start both of them at an initial temperature of 20 degrees, okay, Celsius. And the initial volume is 1 liter, and the initial volume here is also 1 liter. Okay, so if I'm going to call this balloon number 1. I'm going to leave balloon number 1 at 20 degrees. I'm not going to change that temperature at all. What I am going to do to balloon number 2 is I'm going to increase the temperature. I'm going to increase the temperature to 40 degrees Celsius. So think about this as if we had, this is the same kind of thing I've told you about before. If you're early in the morning at a low temperature, you're moving really slow, right? You're not moving super fast. You're going to be slow, not moving really quick before you have breakfast and start working and getting your body moving for the day. But think about how your body feels right after you've played a soccer match, or right after you've worked out or run or done whatever, walked up the stairs even. Your body feels it feels hotter, it feels more energetic, it feels looser, it feels like you can move better, right? So the same thing happens with these gas particles. When we increase the temperature of the gas particles, the particles move faster. This is kinetic theory. We've already talked about this. As we increase the temperature of the particles, as we give them more energy, they move faster. If they're all moving faster, this is how they look when they move faster, apparently. I'm going to give them little tails indicating that they're flying around way faster. What will happen to the inside of that balloon? Well, the inside, they're going to be hitting the container way more, right? They're going to hit the container way more. And what's going to happen is those pressure, or those, excuse me, not pressure, those collisions that the particles are exerting on the balloon is going to cause that balloon to increase in size. It's going, that does not look like it's increased in size at all. Let's do this. It's going to cause the balloon to increase in size. Okay? We still have the same 10 particles, but now they're pushing on the balloon more, causing its volume to increase. Let's say it just doubles. Okay? All right, so this is Charles's law. As we increase the temperature of a gas, we increase the volume as well. And the same thing is true the opposite. If we increase the volume, we also increase the temperature. If we decrease the volume, we decrease the temperature. Okay? Let's look at some example problems here. Or I guess an example problem here. Okay, so let's lay these out because we know we're going to need them. Okay. A 2-liter balloon at room temperature, which is 20 degrees, is placed in the refrigerator at that has a temperature of 3 degrees Celsius. What is the volume of the balloon after it cools in the refrigerator? Okay, so first we have a volume, an initial volume of 2.0 liters, right? And we have an initial temperature of 20 degrees Celsius. It's placed in the refrigerator with a final temperature. What is the volume of the balloon after it cools? So it's going to cool to the same temperature as the refrigerator here. So we are going to have a final temperature of 3.0 degrees Celsius. What is the volume, the final volume of the balloon? We know, oops. I got ahead of myself. Sorry, there's an equation for this one too. You should already know this because of your reading, but my bad, sorry. We're going to go back to where we just were. I totally forgot to give you the equation, I'm sorry. Okay, it would make more sense if I did that. So we have VI over TI is equal to VF over TF. So pretty straightforward. You already had this because you did the reading, but just so you know. So again, this is initial volume and final volume. And then we have initial temp and final temp. All right. And remember, this is a direct relationship, not an inverse like the other one. So this is the second equation. This is Charles's law equation. Whoa. Charles's, it's hard to do that sound. All right. So now the problem will make a lot more sense now that we know the equation, which I didn't realize I gave to you until we got to the equation section that I hadn't given it to you. Sorry, until we got to this section. Okay, now we know which equation we should use. It's Charles's law equation, and you're going to know which one to use based on the things that the knowns and the unknowns that you're given, right? So I wouldn't be able to use Boyle's law for this because I'm not given pressures, I'm given temperatures. So make sure that if you're not sure which equation to use, Boyle's law or Charles's law, make sure you write down all of your knowns and unknowns first, and then you'll be able to see, just based on what you have, what you need to use. All right, we're going to rearrange this so that we have VF isolated. We're going to do that by multiplying each side by TF. Cancels, and I get VI times TF divided by TI is equal to VF. And then we're going to solve. Plug everything in. We have VF is equal to VI, which is 2.0 liters, times TF, which is 3.0 degrees Celsius, divided by our final temperature, our initial temperature, which is 20.0 degrees Celsius. Degrees Celsius cancels and cancels. If you want to verify that you've done this correctly, well, let's give our answer first. So when we do that, we get 0.3 liters is our final volume of the balloon. Okay, let's think about this. We're starting with these two. We're going to decrease our T. If we decrease our T, what must happen to our V? What happens to our volume when we decrease the temperature? Well, because it's a direct relationship, the volume must also decrease, right? So do this after you've done the problem and verify, did your volume decrease or increase? Well, it decreased. Is that what it's supposed to do? Yes, so we're good to go. Okay? Okay. So that is it for chapter 14. We are all done with that chapter. You will have your chapter 14 quiz next Monday. I will post the study guide tomorrow, and we'll do homework corrections tomorrow over all of the homework that we've done in chapter 14. So the assignment that you have today, the 14.3 questions, must be handed in tomorrow before class. There's no chance to not hand it in or hand it in late. It will be a 0 if you hand it in late. So be sure you get it done today or tomorrow before class at least. All right? All right. Please let me know if you have any questions. That is it. Have a good day. Bye.